So now we're on to stoichiometry with standard temperature and pressure conditions. And so standard temperature and pressure, or just STP for short, is like a set of temperature and pressure conditions that serve as like a reference point for measurements. And these conditions are 1 atm and 273 Kelvin, or that's also 0. So that's, yes, because 0 plus 273 equals 273. And so here we're going to be using like Stoic and the ideal gas law. But just remember, you can only use it with a gas. So if the problem is not about gases, then have to use a different strategy. And so again, for Stoic, we're going to need that balanced equation. Just a little reminder. Okay, we're going to have to get these equal. So let's put 3 and 2. Now we have 2Na, so let's get this to 2. And now we have a balanced equation. And then this is going to serve as our mole ratio again. Just a little reminder. So example 1. How many grams of Na3 need to decompose to form 36 liters of N2 gas at a pressure of 1.15 atm and a pressure of 299 K? And so let's set this up like the ideal gas law. So grams, that's the amount, so we're looking for N. R is always 0.0821. The temp they give us is 299. They give us 36 liters and 1.15 atm. And so we're only searching for one thing, so we're going to start with the ideal gas law. So PV equals nRT. That's 1.15 times 36 is equal to N 0.0821 times 299. And when you do all that arithmetic, you get 1.7 mole of N2. But we're searching for grams of Na3. So we're going to have to put that into a Stoic equation. And so that, let's get a mole ratio in to get to Na3. So with our equation here, for every 2 moles of Na3, there are 3 moles of N2. And then we're going to need to convert still to grams. So in every mole of Na3, you can calculate from the periodic table that there are 65.02 grams of Na and 3, and all of that mathed out will be 74 grams of Na and 3 with 2 sig figs, because if you look at the problem, there's 2 for volume given and then 3 for the rest, and so the smallest of that is the 2. All right, let's do another one. What volume of F2 gas measured at 1.10 atm and 308 K is needed to produce 10.6 grams of NaF? So let's set up our little PV nRT again. Again, R is always 0.0821. The temp they give us is 308 K. We're searching for volume. They give us 1.10 for pressure, but they don't give us anything about the moles or the grams. So we're going to start with Stoic to try and get there. Or they give us grams, but they don't give us it in moles. So let's go with 10.6 grams NaF. And according to the periodic table, it's 41.99 grams per mole of NaF. And our final one that we're trying to get to is F2 gas. So let's use that mole ratio that's given here in the equation. For every 2 moles of NaF, there's 1 mole of F2. So all that arithmetic leads to 0.126 mole F2, and there's 3 sig figs in each thing in the problem. So we get 3 here. And so now we can plug that 0.126 into our PV equals nRT ideal gas law. And so 1.10 B equals 0.126, 0.0821, 308. So our final volume there is going to be 290 liters. That's our final answer. What mass of Na metal is needed to react with 1.57 liters of F2 gas at 0.97 atm and 295 K? So P, V, and R, T. Mass, we're searching for N. Given 1.57 liters. Again, R is always 0.0821. Given 295 K and 0.975 ATM. So we can start with our ideal gas law since we're only missing one variable. 0.975 times 1.57 equals N 0.0821, 295, N here. This was all given to us with F2 gas. This is going to be our amount of F2 is 0.0632 mole F2. So we can plug that into Stoich, trying to get to mass of Na. So let's start with our mole ratio. So for every mole F2, there's 2 mole Na. And then in every mole of Na, there's 22.99 grams of Na, which is going to come out to be 2.91 grams of Na.